You're asked to draw a free body diagram. I think that you should. And if I was to consider the forces acting on the person, the first one I would have considered is the fact that there's weight, mg. Person in contact with anything? Sure is. They're in contact with the wall, which must apply a normal force straight outwards. Force on the wall has to be perpendicular to the surface in contact. That's the only possible direction it could act. I don't get to make that choice. So erase yours if you have friction or something else pointed in. That just doesn't make sense. Of course, the only thing then that could keep them from falling or sliding down the wall would be friction, which is a force that would act to prevent you from sliding. Which means these are the three forces that would act on the object, and they would act in this way. Probably the normal force being much bigger than the others. Now, is this a first law problem or a second law problem? Has to be second law. Knew that from the beginning. The only way you travel in a circular path is if you have an unbalanced force acting upon you. Clearly, this is going to be in the x direction. All that work for you guys? So, net force in the x direction equals MAC. That's what the unbalanced force is. Net force in the y direction is going to be equal to 0, suggesting that friction equals weight. Now in the x direction, I only have normal. So normal equals m, well, might as well do this, v squared over r. All right? Has to be a centripetal acceleration. Now, you might not have done it this way, but I would encourage you to begin doing it this way. Friction is an inequality when dealing with the static frictional force. This problem, it's not particularly hard to understand the direction of your inequality, but it won't be like that always. If you want to make sure you understand the direction of your inequality, what should be bigger, what should be smaller, I would encourage you to preserve your inequality. And to do so, substitute into the inequality. So I'm going to put mg, where friction is, mu, and then mv squared over r for the normal force. This way I preserve the inequality. And from here, I'm interested in the coefficient. I'll point out that they don't take your mass when you go on this ride. Anybody can ride it. It's the goal of almost all of your rides. They don't want to have to weigh you before you get on a ride. Some people might find that a bit invasive. So they try to design the rides in such a way that they will fit everybody. And now I just need to get mu s by itself, which is going to be greater than, equal to, looks like gr over v squared. Any questions? Pretty straightforward? Yeah, except for one thing. And at this moment, this is new information for some of you, but not for all of you. This is how fast the person is moving. But that really has nothing to do with the ride, or it isn't directly related to the ride. The ride is an object. Is the ride moving? Is it changing location? No, it's spinning. We tend to describe the ride's speed differently than the person's speed. Because the ride is spinning, the person is revolving. They are revolving about the center. So, although this is true, everything about this is true, it might be better to write this as a rotational speed, something related to the ride, instead of something related to the person. So, if you don't remember this from last year, there is a relationship that ties together the angular velocity and the linear velocity. I'm bringing it up now because I want you to know this. This is that relationship. And I think almost all of you should have had this in your prior physics experience. But if you didn't, this linear velocity is related to how fast the object spins and how far away you are from the center. Just real brief, because I'm looking at phase. I don't think the ride makes sense to discuss it in terms of its linear speed. I think if we want to talk about everybody enjoying the ride, we'd want to figure out, well, how many rotations per second should we make the ride go so that I can make sure most people stick to the wall. Right? That's what this is really about. So be careful. Our problems could easily ask us to figure out the same thing, but in terms of angular velocity versus linear velocity. And just so you guys all are on the same page, this has to be in radians per time to actually use it effectively. Omega has to be in radians per time interval to be utilized effectively. Questions so far? Increase the level of difficulty and trying to read what I think you may or may not know. If we're talking about an object that's spinning, everything on this object has the same angular speed, correct? But which object is actually moving faster? Object 1 or object 2? See, I'm already hearing some disagreement. So, let's say, and this is for the people who don't understand. If you do understand, just be quiet for a minute. For the people who don't understand, let's say this ride goes around once every second. Fair enough? That means I have an angular speed of 1 rotation per second. That would be a rotational speed of 2 pi radians every second. So its rotational speed is about 6 radians per second. Everybody good with that? All right. In 1 second, person 1 makes that circumference. In 1 second, person 2 makes that circumference. Which person had to travel farther in 1 second? Person 1 or person 2? So it should be clear that if 2 people are on the same rotating platform, the one furthest away from the center will be traveling faster. They have different linear speeds, but the same angular speed. Now, if you're an AP problem writer, you understand how you can be manipulating the problem to deal with angular speed versus linear speed. Not because you're trying to be tricky, but because, so again, here's what I want. You're going to swing it. You saw me do this yesterday, right? I want a relationship between the mass hung down the center and how fast you have to spin the stopper. L represents the length of the string from the point where the opening is to where the center of the stopper is. Theta is the angle that it makes with the horizontal. M is the mass of the stopper. Little m is the mass of the stopper. And omega is the angular speed. I'll just remind you that V equals omega times R. In fact, I'll even go one step further, because although this is what we started with yesterday, it should be pretty clear that you could write this in terms of angular speed if you want. I just substituted. All right, give it a shot. So, how many of you start with the free body diagram? Fantastic. So there's my dot. Name a force. Gravity. Should be little. There's not a whole bunch of gravity acting on it. Name another one. Tension. Ooh, tension. All right, let me be careful. Tension. What else? That's right. These are the only forces acting on the stopper. If you do anything else, you did it wrong. And I know some of you did it wrong. Fix it. But I'm not going to wait for you to fix it. I'm going to decide on a coordinate system. And I'm thinking this looks like a reasonable coordinate system. And why this one? Because I need to talk about the component that is towards the center of motion. And by the way, that's theta. So I do think we can break this up into components. And I think this will be t sine theta. And I think this will be t cosine theta. Here's a bit of a stretch. There's two objects. The tension comes from that object, which has a net force of 0. On the other hand, this one has a net force equal to MAC. So from here, I can break this up into the net force in the x direction and the net force in the y direction. X direction is going to be MAC. Y direction is going to be 0. So T sine theta minus mg equals 0. Now, the other side only has the one force. T cosine theta equals MAC. Now, as I've said, and I continue to say, just to make you feel bad about yourself, that's what the steps will do for you. That's all that they will do for you, but that's what they will do. Now, getting to this point, it's not hard. It's what you do from here that might be of issue to you. There's several different ways you can actually go from here, by the way. You done with that chair? Get comfy. And that's on the video now, so we can all listen to it again if we want. Me deciding that a chair is the thing that's going to perhaps unhinge me today. You're all just waiting around to find the thing that unhinges Mr. Shelton that day. You don't have to wait very long. So, I think the next step would probably be to consider this substitution. Does that work for you guys? It's a good way to go. And we're really almost done, aren't we? There's not really much to do now. Except we can't have R. And we can't have T. So we need to make some substitutions for those. So the first thing I'm going to do is substitute in for T, capital MG, cosine theta, equals lowercase m omega squared. Can't have R. I can have L, but L does not equal R. R is from here to here. Looks to me like cosine theta is R over L. How's that? Okay? Fantastic. So now you can get rid of those cosines. And now you know why when we did this lab last year, I didn't make a big deal about the angle. The angle's there, sure. But we can still do this analysis. We can still show that the mass that's hung is related to the square of the velocity. Now, this works if you use angular velocity. This is less effective if you use linear velocity. And that's because if you use linear velocity, the R doesn't go away so easily, the cosine doesn't go away so easily. You're left with a cosine squared theta term. And you should check that out just to make sure you understand where it comes from. It's because when you make that substitution, you have to bring the R back in. By the way, you could also consider finding a relationship between the velocity and the angle. That's actually a little bit interesting. Not super interesting, but a little bit interesting. Consider what would happen if you were to take the information we have in the y direction and compare it to the information we have in the x direction. Do you see something you could do there? So all of you see tan theta equals g over ac. That provides you an interesting relationship. A suggestion that there's a relationship between the velocity and the angle. However, the problem with that is it's not a controllable relationship. It's not like you can spin it faster and change the angle. The speed is still completely dependent on what you hang down the middle. You try and spin it faster, you're going to change the tension, and that's going to change where the weight is. So you don't actually get to choose the angle. The angle is a result of how fast it's going. So in this relationship, the velocity is not something that you have control over. All right. Take a look at any overpass exchange. The one I would call your attention to is the one where the Veterans meets the airport ramps. Do you guys know where I'm talking about? It's a good one. It's a good knot. From the sky, you get a better idea of what I'm trying to impart to you. But you should note that civil engineers and city planners, who are usually the ones who are engaged, when they decide to make a roadway, they try to make the on-ramps and off-ramps, if they have to curve, have circular paths. Now, I know that sounds a little ridiculous, like no kidding, but pay attention very clearly to what I'm about to say. Circular paths, not any curve. They want a circular path so that you should be able to set your steering wheel and not have to change it. Because most drivers have a hard enough time keeping their car in the lane as it is. If the radius of curvature was constantly changing, they would constantly have to be tracking and moving the steering wheel quite a bit. So they try to swing you out away from traffic and then begin a fixed curvature, so you'll stay at that curvature the whole time. This is to make it better for drivers, easier for drivers, so they can be paying attention more to the road conditions, because they might be 40, 50, 80 feet in the air or higher. Falls from those over ramps are almost always fatal. They don't want anybody driving over the embankments. They also don't want anybody sliding off the road. So, interestingly enough, you've probably noticed that all of those ramps are banked. So let's talk about the bank angle of a ramp. Car? Inktober. That's 2 pictures in one day. Thank you. Thank you. I've been trying. I try to draw a little something every day in the month of Inktober. I'm such a horrible artist. I would like to be a better artist, but, alas, I am old dog, no new tricks. So, top down, the car is making a transition. It's driving in a curved path, let's say circular. So this picture is a car that's driving into the board. Does that make sense? So it's driving into the board, it's turning to the left. So this roadway continues out in that direction. Fair enough? Everybody okay so far? They design the bank angle, especially in places where there's snow, to be enough of an angle so that friction isn't necessary to carry the car through the turn. So this problem assumes no friction. What is the relationship between the bank angle and the speed of the car? How many forces act on the car? Two. That's it. That's right. So I have one down. Weight of the car? Normal force. Is this a first law problem or a second law problem? Second, the car is accelerating, but there's less enthusiasm behind that answer, suggesting to me maybe you don't know. But it's definitely a second law problem. Definitely. The only way the car changes direction is if the forces are unbalanced. Now, here's where you might get stuck, and you might want to, do what you've always done. But be careful. We need to look for a component of the force that is directed towards the center of curvature, which means we will need the net force in that direction. We need to find a way to calculate the net force in that direction, because that's what's causing the car to turn, not one up or down the ramp. So if you chose to use up or down the ramp, it doesn't help me too much, because the acceleration that turns the car is directly towards the center. Luckily, there's only two forces here. I didn't make you worry about friction, so there's not a whole lot of work to do. You do have to know that that's theta. Of course it's theta. If it was zero, it'd point straight up. So all of you who are changing yours, phooey on you. Come on, think it through. But I do love watching all of you dive into the eraser. It's kind of nice. Kind of nice. You might want to invest in a new one. I see two forces here, right? What you got, Ava? You got a question? No. Okay. So n cos theta, n sine theta. Questions here? Have I broken away from any of our steps yet? Come on, guys. That's why when I walk by and I see your paper blank, I get frustrated and a little bit concerned about your future in here. Net force in the x direction is equal to MA. It's the only side that's unbalanced. And that has to be MAC, of which there's just one. N sine theta equals MAC. In the y direction, net force in the y direction, definitely going to be zero. That's just going to be normal cos theta equals mg for the car. Seems to me tan theta is AC over G. Can I do that, or do you need me to like step it down a little bit? Good. I'm glad I don't have to step it down. But I will take issue with anybody who used omega here. We would not post a sign for what the rate of rotation of the street would have to be. That doesn't make any sense. The car needs a sign that tells it how fast to go on the curve. That's why they all have a posted sign. So I'm going to get that here. So V squared over R equals G tan theta. Or V is going to be the root of RG tan theta. So you can go either way with this, right? You can solve this for theta and set a posted speed limit. But generally, you have to consider that R is a restraining factor. When they're building the street, they have limited space. So they have to decide R first. How big are they going to be able to build this ramp and still have, enough room all around it for people to drive and put the other streets? And what buildings are already there? When they were doing that ramp over there by the airport, you guys were really little when they redid it all. It's like 8-9 years ago. But they tore all of it down and started fresh and did all sorts of new ramps over there. Believe it or not, you used to not be able to see the water. But they were bringing a Super Bowl and they wanted people to see the water. I doubt that's why they built the new ramps, because that seems pretty short-sighted to do it all for Super Bowl. But it was nice to see the water now. I like seeing the water. So, there you go.